may I ask, thank you. We just heard an excellent ITC colloquium by Rowan Smith. Yeah, somewhere over there. And she will tell us a little more about stars later on at this lunch. We also have a visitor from UC Berkeley, Andrew Siemion, sitting at the end of that table. And he will be the CFA colloquium speaker today. He will tell us about the search for extraterrestrial intelligence, since we are so disappointed that terrestrial intelligence is sufficiently advanced. Maybe they can answer some of the questions that we face, like what is the dark energy, what is the dark matter. So Andrew is the head of the SETI group at Berkeley that was recently funded by the Breakthrough Foundation. And he will tell us a little more during the CFA colloquium about the latest work in collecting data from the GBT and a Green Bank telescope and from HARPS. We will start with Atish Kamble, our own, that will talk about observing proton-proton collisions in young supernovae, and then continue with a visitor from the physics department, Daniel Harlow, over there. And he will tell us about black holes, holography, and quantum information, a very timely subject, especially since we are hoping to establish the Black Hole Initiative here at Harvard within a couple of weeks. And then we'll hear from Andrew Siemion that will tell us about fast radio bursts, searches, detailed emission properties, localization, and fundamental physics. And finally, we'll hear from Rowan again. She's visiting us and will tell us about dark matter annihilation in first stars. Atish.
Thank you. On? I hope so. Okay, good afternoon. Myself, Atish. I worry a lot about supernovae, and I spend much of my time observing them. So I thought I will update you today about some aspects of supernovae which are recently discovered and which might be very relevant to cosmic ray acceleration processes. So this is a work that I have done, and I'm with Maria and Lorenzo, and I'm very happy to say that let it be known that I worked with Greeks and Romans. And this is a beautiful picture of the very large array that was taken by my friend Drew Medlin, who is also responsible for the operation of this array. All right, so why is it important to see proton acceleration, which is also another way of saying why is it important to see proton-proton collisions? Well, this audience does not need to know much about that because they already know. So it's important because it's very important to find the sources of cosmic ray acceleration. Several aspects of the particle acceleration theory can derive a lot. It would be absolutely fantastic if we could actually see the proton-proton collisions, because several assumptions that the theory makes can actually be derived directly from observations. And IceCube has been detecting all these neutrinos. Where do they come from? They might very likely come from proton-proton collisions. And so for all these reasons and several others, it's very important to see proton-proton acceleration. But it's a very hard problem, and a direct way of seeing it through proton synchrotron is ruled out usually because the proton synchrotron is smothered by electron synchrotron. Electron synchrotron is much more powerful than proton synchrotron, and you have no hope of seeing it at similar frequencies as the electrons. So we take another route, and this is very well known, that when you have protons accelerated to very high energies, they are likely to collide and lead to a cascade of secondary particles, such as the pions, charged and neutral pions, which are very unstable. They will produce gamma rays, and the charged pions will produce muons and neutrinos, which will further decay into electrons and neutrinos. If you produce these proton-proton collisions in shock accelerator region, these electrons will get accelerated, and they will produce synchrotron emission. And it's possible that we might be able to see that. So it is this process that we take into account. But for one reason or another, supernovae are not considered as the most efficient way of doing this, because they lack enough density. So the bottleneck here with the supernovae is this, that the proton-proton collision timescale is very long for typical CSM densities of 1 particle per centimeter cube. It takes about 35 million years for 2 protons to collide. But if you have high enough density around the shock, then it might be possible. So we have recently discovered new supernovae which might have enough material around them, and in that case the optical depth to proton-proton collision could be significant, and it might produce observable effects. So as you can see, even at a distance of 10 to the power 16 centimeter for a typical shock of 5,000 kilometers per second in a supernova, you have optical depth which is still significant, and this would typically correspond to several months to a year in a supernova's life. So what I'm talking about are the young supernovae. And if you could see this process, it will have a very distinct signature, that the injection Lorentz factor of those electrons would depend on the mass of the pion and electron. So it will have an injection around gamma of 70. And you should be able to see this signature. So this is a morphology or a structure of supernova. The way they are discovered is through this optical emission, which is typically at 6,000 Kelvin. But there is also a much faster shock wave, which races ahead, and it has a much higher temperature, 10 to the power 9 Kelvin, where the electrons gyrate in the shock amplified magnetic field, and they generate synchrotron emission, which is what we see. It also produces reverse shock, and which is at a 10 to the power 7 Kelvin, which is where we see X-rays. So the idea is that if you have high density material around the supernova shock, you might get away with all the adiabatic losses, and you might be able to convert all that supernova energy into radiation effectively. So let's bring supernovae back to the focus as cosmic ray accelerators. They have all these good properties: large energy output, strong shocks, efficient particle accelerators. They have dense environment around them. Even from the typical supernovae that we have seen, there is a large range of mass loss rates that we have seen. And these are some of the recent developments that we have seen: interaction-powered supernovae. They're also called as the superluminous supernovae. And here I could find one slide of their light curves. So this is the recent one, 15 LH, which is extremely bright. And the way to make it so luminous is that you have a lot of material around it so that the shock energy gets converted into radiation. Well, the other way is, if you want to get around the adiabatic losses, you put a magnet out there. But it might be possible to distinguish between these features using the processes that I'm talking. And I know that many of you may not actually care for the final result, but how one gets there. So I'll give you a brief recipe and the ingredients. So what we use is a freely expanding shock wave in the supernova. In the wind medium, you have particle injection, which is a power law in energy with exponential cutoff. All the cooling processes that we take into account are adiabatic, synchrotron, and inverse Compton losses. Then you have radiation due to synchrotron and absorption due to free pre-absorption in the hot ionized wind. And the PP cross-section that we take is one of the most updated one. That's from Kellner et al. And with all these things, we start cooking and hoping for the result to be delicious, but it could be disastrous also. And so here is the result. So these red lines are the proton distribution in log-log scale. This is log of gamma, Lorentz factor versus gamma square n gamma. So you have all these protons going from R 10 to the power 13 to 17. You can see that the total number of protons keeps going up linearly. And there's an exponential cutoff, which is sitting here. Then the blue lines are the primary electrons. At the time of shock breakout, which is at say 10 to the power 13 centimeter, you have all the electrons cooled. And as the time progresses, you can see that the cooling break is moving up. And then you use these protons and the updated PP collision cross-section to calculate secondary electrons. And now the blue lines are the secondary electrons. Because they are generated from the protons, which are highly energetic, you can see that their Lorentz factor is very high. they don't need reacceleration as such. And the injection frequency that I was talking about at about 100 Lorentz factor, this is where it comes up. This entirely depends on the mass of pion and mass of electron. So you can see this signature. And then all the cooled electrons then accumulate at lower energies, generating this power law distribution here. So you could use this distribution and use the same shock amplified magnetic field to generate the synchrotron emission. And this is what we see for typical parameters. It starts from 2 days, then I plot at various different times. So at 2 days, the red line is the primary electron synchrotron emission, the blue line is the secondary, and the total synchrotron is the black line. So you can see that at 2 days, the red line is much below the blue, which is the primary emission is much low, and the secondary is dominant at early times. As you go forward, the primary emission, which is the red line, starts to dominate over the secondary emission. But the point is, up to about 100 days or so, the secondaries still dominate. And it would be possible to see this emission directly. And these are the light curves. Once again, you have the red line, which is the primary, and the blue is the secondary. This is at 10 gigahertz, so VLA typical observing frequencies. And you can see that the secondary emission dominates at early times. These are still very low frequencies. As we go to higher frequency, you can see that the emission starts rising at early times, and the secondaries dominate even higher. If you go to 1000 gigahertz, which is just above the ALMA band, so within ALMA band, you can see that at early times, the secondary emission would be much brighter. And it would be absolutely fantastic if you could see this. This is the current status of observations of radio supernovae of the kind type 2Ns and superluminous supernovae. The upper limits are up there, and nobody has actually probed them where they should be probed, at high frequencies and at correct times. So these, once again, the red lines are the total emission from the synchrotron emission. The blue line is the secondary emission, which dominates at early times. And the KEPs, which is the most important parameter in particle acceleration, for different values, you can distinguish different light curves. So typical sensitivities of the instruments today are here, and if we could probe at this level, we should be able to see this. We should be able to distinguish this. And with that, well, thanks. Yes.
Can you use those to calibrate some parameters in your model?
Yes, absolutely. So it is true that we do see gamma rays from galactic supernovae, and we can also use Fermi to see what the gamma ray background is using these sources. I would say just hold on, because we are writing that paper. And unfortunately, I don't have the slide to show you right now, but I can talk to you later.
Questions for Atish? Other questions? It looks like you did a great job.
Thank you.
Thank you.
Let me make this.
All right. All right. Hi. So thanks for the invitation to speak here. I just came from down the road, so not very far. I guess it's a bit unusual title for a CFA, but I guess we all like black holes, so that's good. I'll just try and give you some sense of what the issues are. I'm not, obviously going to be able to say anything about the details, but hopefully at least to convey that these are fun things to think about. Okay, black holes are very interesting, obviously. Here are two pictures that I like that show that black holes are real things, not just things that string theorists sit around and think about. Right? This is the black hole in the center of, I think, M87, and I guess we all know what this is. Now, classically, we understand black holes quite well. If you look right here in these things from LIGO, right, this is theory, and the data is the gray thing, and this comes from solving the equations of general relativity numerically. So classically, black holes are in some sense not mysterious, but quantum mechanically, they are very mysterious. In fact, maybe it's not widely appreciated. Black holes really are the main problem that's kept us from finding a theory of quantum gravity. Here we are in 2016, 100 years after general relativity, we still don't have a quantum theory of gravity. And it's really because of black holes. Black holes prevent us from defining the kinds of observables that we talk about in quantum field theory, which is the thing we use to understand all of the other forces. So you can actually be quantitative about that. Usually when you talk about defining localized observables in relativity, you talk about rods and clocks, right? Setting up a network of rods and clocks. But say you wanted to set up a network of rods where the spacing between the rods was of order the Planck scale, which is the kind of thing you would have to do if you wanted to have a quantum field theory of gravity. That doesn't work because you need your collection of rods to not be a black hole. And if you think about it for a sec, you convince yourself that that means that each rod has to be light compared to the Planck mass. But you also want to have some idea where your rods are. You don't want them to be fluctuating all over the place because of the uncertainty principle. And if you think about that for a minute or two, you'll convince yourself that that requires the masses of the rods to be large in Planck units. So there's really no way of defining the kinds of observables that we usually measure when we're talking about Planck scale physics. And it's essential for this argument, of course, that everything gravitates, right? That's the special thing about gravity compared to electromagnetism or something, right? If this were electromagnetism, we could just make the rods be neutral, and then you wouldn't have to worry about this. Right? This problem is most precisely illustrated, I think, by this famous Bekenstein-Hawking formula for the entropy of a black hole. So here S is the entropy, A is the area of the horizon of the black hole, G is Newton's constant. And then there's some C's and H bars, which I've, of course, set to 1, like any civilized person. Now, the interesting thing here is that the entropy is not extensive, right? Like if you have a thermal gas, the entropy grows like the volume. So we call that extensive. And that's what happens in quantum field theories, right? Quantum field theories, you have degrees of freedom at each point in space, and so the number of degrees of freedom grows like the volume. But here it's only growing like the area, and roughly speaking, this has to do with this idea that, if we try and define all these degrees of freedom, we get into trouble. The black hole cuts you off before you can really find all of them. So this really suggests that a theory of quantum gravity is going to be quite different from how we think about the other forces. Inspired by this Bekenstein-Hawking formula, these people proposed the so-called holographic principle, which says that if you have a theory of quantum gravity, and I guess this should have been space-time, although I guess this statement doesn't matter. I was thinking space-time. D space-time dimension. You should really think of it as a theory that's local in a lower number of dimensions. That's kind of what this suggests, right? You should sort of go down by a number of dimensions to explain this. Go down by one dimension to explain this formula. Now, this might sound totally crazy, but in fact, by now we have two very well understood examples of the holographic principle in action. So one which I won't really talk about is called the BFSS matrix model. It uses quantum mechanics, which is in 0 + 1 dimensions, to describe 11-dimensional flat space. So that's very holographic. Probably the more well-known example, which I will discuss, is this ADS-CFT correspondence. That's anti-de Sitter conformal field theory, which says that a conformal field theory, which is just a special kind of quantum field theory that is also invariant under scaling transformations, is actually equivalent to a gravity theory that's in at least d + 1 dimensions. And so this is discovered by Maldacena back in the late 90s. But I mean, still, how can this be true? This is crazy, right? How can a theory in one number of dimensions be equal to a theory in another number of dimensions? I mean, to claim to understand this, we have to be able to get some understanding of how that works. So let me just say a little bit specifically about the ADS-CFT example. So anti-de Sitter space is like a can of soup, where the anti-de Sitter space is like the soup inside of the can. And then the CFT is sort of living on the metal at the boundary of the can. So time is going up in this picture. So both the CFT and the gravity have time, and also this angular direction. But then this radial direction here has to somehow be emergent, right? In the conformal field theory living on the boundary, you don't have this radial direction. So this is sometimes called gravity in a box, because in anti-de Sitter space, if you throw a baseball away from you as hard as you can, it goes away for a while and then it comes back to you in a time of order the ADS radius. So that's the negative cosmological constant, right? If it was positive, it would accelerate away from you faster. It's embarrassing that it's negative, but sorry. Right, so there's the CFT. And the CFT is a quantum mechanical theory. It has unitary time evolution. So if you make a black hole and it evaporates, that'll be a unitary process, contrary to what Hawking says. So that's exciting. But still, where does this extra dimension come from, right? It still seems kind of crazy. Okay. So in fact, the craziness can be sharpened into a paradox, into a mathematical paradox. So in any quantum field theory, usually causality is the statement that fields that are space-like separated commute with each other, right? Because if they didn't, then if I measured one of them, then it would affect what I got from measuring the other one, and that would be a telephone, right? I mean, that would be communicating faster than light. That can't be. So this is how quantum field theory imposes causality. Now, you can think about that in the bulk, right? So here's my ADS, and now I've got a field sitting there in the center of the bulk, and then I've got some field sitting at the boundary. So since it's at the boundary, I call it O instead of phi. And then you might think, well, since these guys are space-like separated in the bulk in the radial direction, they should be commuting operators to preserve causality. But that's actually impossible. In a quantum field theory, that would require that you had some operator here that commuted with all the local operators in the boundary theory, and that's in quantum field theory. There's a theorem. You can't have that. So it's a theorem that says very sharply that a quantum field theory in d + 1 dimensions can't be equal to quantum field theory in d dimensions. Okay. So maybe it's okay because it's gravity in the bulk. It's not quantum field theory, right? That was the whole point before. But somehow we're going to have to use that fact that it's gravity to escape this kind of paradox. There's a related paradox saying that, so now this circle here is like I'm taking this disk here and just looking at it from the top. So we're just looking at a time slice in the bulk from the top. So there's a simple way of arguing that if you have a field, so if I give you access to a subregion of the boundary, right? So this A here is like, a time slice of the boundary is like this circle here. And so then A is like an interval in the circle. That's a subregion of the boundary. And so then you can argue using standard physics in the bulk that if you have a field that's within, so if you draw a circle here, if you have a field within the circle, then you can represent it in the quantum field theory, in the conformal field theory, it's an operator just living in this A. But then that's clearly non-unique, right? Because I could have picked A like this or like that. And actually you can get into these funny situations where you have a field in the center and you can't represent it on A or B or C. Any one of them by themselves have no information about, say, whether you acted with the field or not. But any two of them do, right? Because A and B together, now if you draw the circle, it's inside of the wedge. So this is kind of funny. The information is somehow very non-locally distributed in the boundary theory in this sort of redundant way. So in the last 2 years, we've understood that these kind of funny features of holography can really be understood by interpreting the correspondence as what's called a quantum error correcting code, which is something that probably most of you have never heard of, but it's something that people who are trying to build quantum computers have to worry about all the time, because when you're trying to build a quantum computer, your memory is getting decohered by the environment, and you want to stop it. So, as predicted, I was going to run out of time right there, so I'll just show you some fun pictures. So in this picture, in this theory of quantum error correction, what happens is that this radial direction gets reinterpreted as a quantification of how well protected information is. So information near the boundary is badly protected. There's small erasures can delete it. Information in the center is very well protected. And similarly, the way you avoid these commutator puzzles is exactly by the formation of black holes as suggested earlier. So if you try to protect too much information at once, then you find that you form a black hole. And that's what enables the resolution of the commutator puzzle that I mentioned before. So there are explicit solvable examples of this. These are sort of the Ising models for quantum gravity that were discovered in the last few years. They look cool, so I thought I'd show them. It's basically the same as these, but now these are really precise. These all mean things that you can compute. And they're new error-correcting codes that were discovered. So maybe they're good for something. I don't know. Maybe in 30 years, when you have a quantum computer in your cell phone, the reason that it won't be decohered by the environment is because it's simulating quantum gravity in anti-de Sitter space. All right. Thanks. Well, yeah, it's very inconvenient from this point of view, yes. Yeah, so the details of using the CFT and stuff, yes, would have to be different. So, all I can say is that this fact that you can put gravity inside of a box is very convenient, because you can sort of keep the funny business in the center where you can keep your eye on it, and you can sort of keep things controlled out at the boundary, and that makes it much easier to formulate these things mathematically. Whereas in de Sitter space, you're smack in the middle of everything, and there's a CMB and a Big Bang, and you have to deal with everything at once. So yeah, of course, but you're not trying to do it with complete quantum mechanical precision. So we have to. If you like, it's a simple harmonic oscillator of quantum gravity. And so we have to first understand the simple harmonic oscillator. Before we can do helium or something.
So not to be prosaic after such a presentation, but does this have any implications for the observable properties of black holes?
Unclear. So it also depends which black holes you're talking about. So with astrophysical black holes, I would guess not. Now there are people who try and argue that. Well, there are various paradoxes which I didn't discuss where people are confused about how to represent the interiors of black holes. And some of the proposed resolutions involve modifying the geometry outside of the horizon. And so, once you start trying to play that game, pictures like this one start being problematic for you. And then certainly also with the Event Horizon telescope, when that comes online, we'll also test some of those theories. Now, personally, I think those theories are wrong anyway. So I won't be surprised when they get ruled out. But I think that the things that are better motivated are going to be hard to test astrophysically in the short term. I think a better way of thinking about this is that if someone comes to you on this, this is really a theoretical test for theories of quantum gravity. You should think of this in the same way that Einstein thought about trains moving at the speed of light. There are things you use to understand the theory better, even though we still don't have trains moving at the speed of light, right? But I hope one day that we will find, and that theory, of course, ended up having all sorts of predictions, which Einstein didn't know about when he was thinking about the trains, and hopefully it'll be similar here too. Yes?
How does this work affect Hawking radiation?
Yes, it affects it a lot. So yeah. So not in the sense, of course, that saying Hawking is wrong, but in the sense that in Hawking radiation, in Hawking's calculation, the radiation is purely thermal, like as a quantum mechanical statement, like e to the minus beta h is the state of the Hawking radiation. And that's not what happens when you burn coal, right? What happens, like if you burn a lump of coal, is that it looks like that if you don't look too carefully, but then if you look more carefully, there's actually subtle correlations between the heat, and the smoke and the ash, which tell you, where the coal was dug up or this kind of thing, right? And so in ADS-CFT, it makes it more like coal. So in ADS-CFT, the Hawking radiation in the end will be unitary. So it will come out in a pure state. And so that says that Hawking, in some sense, must have been wrong about the very precise details of the calculation. But this is something we're still fighting about. So, okay, if he's wrong, okay, which line of the calculation did he make the mistake in? I mean, people are still fighting about these things. Yeah, that's true. Yeah, he will be here. So, I mean, he thinks he was wrong too, though, so it won't be hard to convince him. No, he doesn't know either. Yeah.
This may be just another way of asking the question that Erwin just asked, but what happens to information content when black holes evaporate?
Yeah. So the idea here is that it comes out. So because the conformal field theory is it's never mind, it's a quantum field theory. It's like the harmonic oscillator. I mean, there's some Hilbert space and some Hamiltonian, and it's evolving in a unitary manner.
So the information is preserved, but it is radiated away. So
yeah, into the Hawking radiation. That's right. And so there's nothing left. There's no remnant or anything like that, if that's what you're asking. Yeah.
Thank you so much. That was fascinating.
Sure. I have to give you this. Here we go.
Well, thanks very much for having me. I'm very excited to be here. This is actually my first trip to the CFA, so I'm having a lot of fun already. As Avi said, I spend most of my time thinking about the search for little green men, but I did some of my PhD work on fast radio bursts, and they still hold a soft spot in my heart. So I wanted to talk a little bit about what we're doing with fast radio bursts, and of course this is work that I'm doing with a whole bunch of colleagues from all over the place, notably some folks at Green Bank Observatory and also Aris Karasteragiu's group at the University of Oxford. So what I call the sort of saga of fast radio bursts, or the saga of Lorimer bursts, began with this plot. This was from a paper in 2007 by Duncan Lorimer in Science, and many of you have probably seen this plot before, but if not, I'll sort of walk you through it. On the y-axis here is frequency. This is radio frequency at L band from about 1.1 to 1.5 gigahertz. This is time in milliseconds. And what we see here is intensity indicated on this plot, a lot of intensity in a short period of time, a few milliseconds wide. And it shows this quadratic dispersive sweep that indicates that probably whatever caused this pulse traveled through a large amount of cold plasma in interstellar space. But based on the direction of where this pulse was pointed, the amount of this dispersion that we see in this plot that can be accounted for by our Milky Way galaxy is only about 10%. And so the inference is that because this pulse had such a large dispersion measure, this pulse must have traveled through a large amount of intergalactic space. And so this pulse looks very much like a pulsar pulse, and in many respects it's identical to a pulse that we might see from a pulsar. But the difference is that this pulse was only seen one time. In nearly 100 hours of reobservation of this pointing, it was only seen once. And so that, combined with the inference that it was of an intergalactic nature, really started a huge amount of speculation as to what could have produced this very, very bright pulse. And the extrapolated distance, again, this is pretty uncertain, was that this thing could have come from up to a gigaparsec away. And it's very, very bright. This was detected with the Parkes telescope, and it's pretty high signal to noise. So it was a huge amount of energy in a very short period of time from a very long way away. And this brought about quite a lot of consternation. And I have my own favorite way of describing the consternation here by plotting astronomer happiness versus time. So Duncan Lorimer announced this in 2007, an intergalactic millisecond burst in science. Of course, everybody wanted to follow up on these things. Julia Deneva and others conducted a search at Arecibo, didn't find any. Sarah Burke-Spillar conducted a search at Parkes, and she found some things that looked suspiciously like fast radio bursts, but occurred in every single beam of their multi-beam receiver, which is, as far as we know, an unmistakable indicator of the pulses being terrestrial in nature. She called these peritons. These are the things that were eventually determined to come from microwave ovens. There were non-detections at the Allen Telescope Array, some work that I did, and also at the Green Bank Telescope. And so around 2011, 2012, people were getting very, very sad. Evan Keane announced a new detection in 2011, but the DM here was actually pretty close to what would be expected for the Milky Way contribution to the pulse, based on its pointing. So there was kind of some hope, but not a lot. And then, of course, everything changed in 2013 when Doug Thornton had another paper in Science where he identified an entire population of these bursts, all detected with the Parkes Observatory. But then, even after that, there were still some questions, and even Avi had some questions about it, that these might be originating with flaring stars. So rather than the large dispersion coming from some intergalactic contribution, perhaps it just came from some very dense plasma that was near the source. There was an Arecibo detection from Spitler, but again, Shri Kulkarni also had his doubts as well. So if you're sort of familiar with this field, you know that a lot has happened in the last year, and certainly it has. Emily Petrov announced the first detection of one of these bursts in real time. The time between the actual recording of the data and the detection of the burst for that Lorimer burst was almost a decade. And the time between detection of the burst, recording of the data, and actually identifying the burst in the data for Emily's work just last year was about 2 minutes. So we're finding these things much, much faster. There's been several other bursts that have been found with Parkes. Vikram Ravi had an interesting paper where he claimed to associate a burst with the Carina galaxy. This paper here by Masui et al., this was the first detection of an FRB with the Green Bank telescope. One, a brand new telescope. Two, it was detected at 800 megahertz, so with a different receiver, not at L-band. And then just in the last few weeks, there have been a number of very interesting papers. Evan Keane had a paper in Nature where he claimed to see an afterglow. This is sort of subject of a bit of additional consternation, this particular burst now. Laura Spitler announced that she had found additional pulses from the one that she had detected at Arecibo. She found about 10 additional pulses. And then just most recently, a couple of days ago, Paul Schultz did some follow-up on this same repeating fast radio burst with the Green Bank telescope. And this is really a fantastic plot showing all the work that's gone into this. Over here, number one, this is the initial detection of the pulse with Arecibo. These are follow-up observations with a whole bunch of different telescopes, both radio and high energy. Each one of these little dots here indicates an observation, and the ones with the circles indicate that there's been a detection. And so there's a lot of non-detections here, of course. This is a very weak burst. It was detected at only like about an SNR of 20 or so with Arecibo initially, so it's pretty weak. But importantly, it was detected at 2 different telescopes. And this really has kind of closed the book on these bursts being some kind of terrestrial interference. They've been detected with 2 different telescopes at the same dispersion measure, and that's of course very, very exciting. Also interesting are the detections themselves that have been made with both Green Bank and Arecibo. So these are S-band observations. So these are at a higher frequency than the initial detection, and you see several detections here. And there's quite a lot going on here, but I think the most interesting bit about this, at least as far as I'm concerned, is the tremendous amount of phenomenology that's shown in these plots. They tend to have quite varying spectral indices, varying fluxes. And another thing, of course, that sort of comes out of this is that some of the suggestions that were initially made about what might cause fast radio bursts is that it might have been some kind of cataclysmic event, some kind of massive object coalescence, or some kind of a gamma ray burst or supernova-like cataclysmic event. But because this burst is repeating, it certainly leads one to believe that there must be some kind of sort of repetitive process, of course, that's involved in creating them. And so these tend to sort of push us towards some kind of a very, very young pulsar, magnetar explanation for what causes fast radio bursts.
These are dispersion collected already?
Yeah, that's correct. Yeah, so this has I think a DM of about 550 or so, and the dispersion has already been removed here. I sort of ran out of emoticons to describe sort of what's happening out here, but there's quite a lot happening. Certainly, lots of these things are being detected, but we have quite a lot left to do, I think. We're still very much hampered by the low number statistics here. We've only detected 22 sources. That's sort of my number. I don't know if that's the most accurate number. People be a little cagey about their fast radio burst detections, but certainly we don't have a whole lot of them, and so that impairs our ability to infer much about the population. And one example of that was the claim that there was some integer spacing in the dispersion measures of these things that was made a couple of years ago, which has been very much refuted now. But really what we need to get is more information about these things. What we typically have is just Stokes eye data, perhaps integrated for 500 microseconds or a millisecond. So getting polarization information is very, very useful, and we're starting to do that now. But the most important thing really is to get the location. And this is maybe not something that's obvious to people that aren't radio astronomers, but a telescope like the Parkes telescope at L-band has a beam size on the sky of something like 20 arc minutes or 15 arc minutes. It's a huge amount of sky. And even Arecibo can only get a localization with a single beam of the multi-beam receiver to about 3 arc minutes or so. So getting very, very good localization is going to be very, very important. And of course, the most obvious way of doing that is with an interferometer. And there's an instrumentation technology that's really enabling a lot more fast radio burst searches to be considered on interferometers. And really that comes from the fact that correlators that actually process the data from interferometers are becoming very, very flexible. And this is just a schematic diagram of a new correlator that we actually designed at Berkeley, but it illustrates how many correlators are being designed now, which is rather than having some static bit of computational fabric that does some particular modes and some very sort of specific things with the instrument, they're very, very flexible. And so you just digitize some data and you feed it into some Ethernet switches, and then you can connect all kinds of interesting things on the end of it, maybe some disk arrays or some graphics processing units or some multi-core CPUs. And this enables you to use correlators in ways that have never been done before. Is that really my time? No? Okay. Well, I guess I'm going to go very quickly then. Also, a lot of very interesting things happening on single dish backends similarly. And so I'll just sort of go through a laundry list of these projects quickly. Casey Law and Sarah Burke-Spillar and others, including myself, are working on something called Real Fast at the VLA. This is doing very, very fast imaging with the VLA, about 128 megahertz or so. We have a project using the EVN that Zsolt Pierogi at Jive is leading that's allowing us to do a commensal search on all EVN observations for fast radio bursts. The sensitivity here is not great, but we're hopeful maybe 1 or 2 bursts could come out of this. This is just for all the theory people, since this is the Institute of Theory. This is why doing this is hard. These are 9 different telescopes in the EVN looking at the same source, and as you can see, the kind of data that we get from these telescopes is very, very different, all kinds of diverse interference, which really is what makes it very difficult to detect these. We recently commissioned 2 commensal fast radio burst searches, one at Arecibo called Alpha Burst. We just got some data from that. This operates in real time, and another kind of copy of that called Green Burst at Greenbank. The really cool thing about this is that we actually get a signal from the L-band receiver at Greenbank anytime the telescope is running. So not just when that receiver is in focus, but anytime the telescope is observing with any receiver. So we get lots and lots of time on the sky. And this is my last slide. We think maybe 5 to 10 a year with Greenbank, 2 to 3 a year at Arecibo. Raw voltage data and real-time detection. So we're going to find out about these really, really quickly, and we're going to have lots of information about them. Thanks. Yeah, well, that's because I don't really believe that possibility very much. I think this has been suggested. As you said, Avi, there are still a few holdouts that bring this up. I think the fact that we detect these things at many different directions on the sky is a pretty strong indicator that either the aliens are all conspiring with one another about their signal types, or this is some kind of natural phenomena. My vote's for natural on this one.
So for the one that had a potential afterglow association, there's been some question as to whether that's genuinely associated with the radio burst or whether that's just resulting from a radio AGN.
Yeah.
But one thing that struck me was that there is a coincidence that there happens to be a radio AGN in the beam where that fast radio burst is located. For this one, the one that's had many repetitions has been seen in Arecibo and at Green Bank. Is there any sort of AGN like that sitting in the same beam?
As far as I know, the answer to that is no. But this is certainly something that's a subject of quite a lot of follow-up observations, even deeper than what was done before the paper was announced. So I'm not sure, but as far as I know, the answer is no.
James, the expected number for radio AGN within a parts beam is order unity, so I don't know why you're surprised.
What about for Green Bank?
What's it, a half or a quarter or something?
It's the size of the wavelength of the size of the dish, which is roughly 10 arc minutes. That's the diffraction limit of all these data. Well, if there are no more questions, let's think and
Hey, we have light. Excellent. So hello. So when I was giving this talk, they said do something completely different. We're going to do an ITC colloquium, so we want to hear something completely different. So I'm afraid that's what you're getting. Because a few years ago, I did this really cool project. When we're looking at star formation, the first stars to form after the Big Bang in the early universe, well, that's quite a different situation to the stars that form today. So in the present day, star formation is really messy. You have all these molecular clouds that are a turbulent mess. You have all this substructure. So knowing the initial conditions is really hard. However, when you go back to the primordial universe, everything is really simple. You have these beautiful dark matter halos. They're smooth, they're centrally condensed, and you know that the star is going to form right at the centre of them. However, of course, that means there is a complication. So I put up here a nice simulation by Paul Clark in 2011, published in Science, where he did some simulations with work in Thomas Greif, who used to be here as well, looking at the formation of the first star in one of these halos. So up here, right at the centre, is a cosmological halo. Within the very central region, we get one single object forming, a disk building up around it, and then over time, this disk fragments to form multiple stars. And so you have this beautiful disk at the centre of your dark matter halo, which is fragmenting to form a small cluster by disk fragmentation. And this was a bit of a new result at the time, because everyone thought population 3 stars were probably big, single, isolated objects. But instead, we see here there can be fragmentation. And of course, where you have fragmentation in close proximity, and this is only a 40 AU disk, you can get ejections. So this means you could even get low mass stars. But of course, there is one complication. From the beginning, I've said this is happening at the centre of a dark matter halo. And of course, we think that dark matter probably self-annihilates. Which means right at the centre of this region, we have this huge source of energy, which is occurring at the same place as the central star will form. And this has read a number of people, for example, Swallow et al. In 2008, predicted that due to this effect, you could get these exotic objects called dark stars. And what essentially would happen was at number densities of 10 to the 13, the energy from this dark matter annihilation would overcome the cooling rate you can get from H2 line cooling. And so you would get gas supported at this density purely by the energy of the dark matter annihilation from the potential within. So this was a bit of an exciting prediction. We have all sorts of implications for our understanding of the early universe and what you might see with the James Webb Space Telescope. And so one of the things which I and my collaborators, this is some earlier work by Rick and Monty et al. In one day, wanted to look at is, actually, if you look at the chemistry of the primordial universe in one of these halos, does this happen? Do you get dark matter supported stars? So this is the process we went through. We took a cosmological simulation from Thomas Greif, and we used an analytic model of the dark matter potential. And this is contracting adiabatically, as is predicted from the literature. And we assumed that a third of the energy escaped through neutrinos, and the remainder would be split between heating and the ionization of material within it, according to Valdez and Herrera. The extra heating from this annihilation is then added to a primordial chemical network from Paul Clark in 2011. So the main effects of dark matter annihilation in terms of the chemistry is, first of all, to heat the gas, but you also get this ionization. So we ionize hydrogen, we ionize helium, helium plus, and deuterium, and you can dissociate the H2, HD, and H2 plus. And so the dark matter annihilation can affect the temperature in two ways: by the direct heating of the gas and by the destruction of H2 molecules at high densities. It also can cool the gas by having an increased amount of molecular hydrogen at low densities. And of course, in the primordial universe, H2 is your primary coolant. So to go to the results of our little calculations, I've just shown at the top here a radial profile going outwards in these primordial halos, which I've just averaged radially. They are 3D simulations, but that's kind of hard to show in a simple plot. Grey shows you the gas density. Black is the average of this, and red is what you're getting without annihilation, and the blue just shows you the dark matter profile. Now, it was predicted by Swallow et al. That you would not be able to get densities above number density of 10 to the 13th. Now, as you can see right away, actually when you don't have the full chemistry, you're not getting this effect. Instead, the gas is still able to collapse to high densities to form a star, a normal star, not a dark star at the centre. The only real difference is that you get this little bump here. That's kind of strange. You have all this energy from dark matter annihilation at the centre of the halo, and yet it's not really doing anything to your density profile. And so we had to wonder out, why is it this huge amount of dark matter is not affecting the gas density, the gas dynamics, more than it was? In fact, we found that the gas actually collapsed faster when there was dark matter annihilation included in the calculation. Well, if we look at the temperature here, this is with the dark matter annihilation, and this is without. And we can see the temperature is very different. And the outside of the halo is cooler because the extra ionization made it easier to form H2. So you were cooler in the outer of the halo. And in the inner, you're much hotter due to this dark matter annihilation. There's something a bit weird. You can see this really flat profile. So the temperature gets so hot, and then it just can't get any hotter. And so this is what's stopping the dark star from forming. So we looked into this a bit more, looking at the heating and cooling rates, which I break down here. So up here, on your right, we have the reference case, which doesn't have any dark matter annihilation. And on your left, we have the case with. So this heating rate here, shown in black, is the dark matter annihilation heating. Now, if we look at it, we can see there is one very strong difference. And that's in this case, we have these huge increase in these rates, which are shown in blue and in purple, compared to the reference case. And what this is this is the collisional dissociation of H2. And so what we find is because of the hotter, denser conditions, the H2 at the very centre begins to bounce into each other. And this causes it to collisionally dissociate. Now, in order to break the bond of H2, that takes energy. And so what's happening is that instead of heating up the gas, all this energy from the dark matter annihilation is being used to break the H2 bond instead. And so if we look at the timescales for this, just look at the energetics at the densest point in our calculation before we ran out of resolution. You look at the amount of energy needed to dissociate H2 at these densities. It's about 1400 ergs per centimetre cubed. Now, at these densities, given the amount of H2 we have in the gas and the energy of that bond, we see that it would take about 10 years to dissociate all this H2 material. If we look at the free fall time of the gas at those densities, we find it's about 2 years. And so it's due to this breaking of the energy of the bond that you cannot form a dark star in this one set. So that was a bit of a shame. But just to, because it was a kind of fun object, and we all like the idea of it. And this paper isn't tremendously cited because the worst thing you can do is say, this doesn't really happen. So if any of you feel like rectifying that, really go for it. But the interesting thing that we did find was that I carried on the calculation. So just with a normal sink at the centre, which we assume is just a normal star, we carried on the calculation and looked at the disk which formed around the central object. Now, on the right is what we found before. Every bit where you find a little white dot is where you have a protostar. And so you can see this disk is fragmenting. However, if you look over here, with the dark matter annihilation, this extra heating has increased the temperature, it's increased the gene's mass, it's made the disk smoother. And so we no longer have the same fragmentation of the disk. And so whether we have multiple systems in the early universe, you probably need to take the dark matter annihilation into account to see whether that's true or not. Later on we did find some fragmentation, but it happened at distances of over 10,000 AU. So it's a significantly different regime. So this is something to bear into account, a new regime of star formation. Another interesting thing to think about star formation in the early universe. Thank you.
Is this as analogous to suppressing fragmentation with radiative feedback in modern star formation?
Very much so.
Okay.
Yeah. Yeah, I mean, you can pick what is it. I mean, whether it's like, if it doesn't self-annihilate, none of this works. And then if you look at the mass of the dark matter particle, we did a couple of different masses. So this is with 100 GeV dark matter. You have 10, then obviously you get stronger signals, so this will be even stronger. If you have anything much larger than that, there won't be enough heating from the annihilation to have much effect.
Other questions? No, thank you very much, and that's it for now.
Andrew?
Yes.
So the question for like if there's any radio galaxy kind of breadth, what do you think about Ito's claim that there's one for?
I think that that's probably a little high. but maybe only by a factor of 5 or something. I think sort of to say its order unity is probably a fair thing to say. The story that I heard was that initially that paper had something sort of much more conservative for the likelihood of that being an association, like something like 1 in 15 or 1 in 20. And then they found some like transient rate somewhere in some paper like right before it went to press, and then they changed it to like 1 in 100 or something. So, I mean, I don't know if it's an afterglow or an AGN. I think the jury's kind of still out. But I think, it's possible. But it was probably stated a little strongly controversial.
I mean, the repeater at least shows the same phenomenology, but easier because the DM is slower.
Yeah, I mean, the weird thing is that if you believe that that's an association, there's a known redshift to that galaxy. The sort of density that you come up with is kind of the right answer, sort of the expected density.
Yeah, Peter Williams gave a talk where he showed like a histogram of DMs that you would get at that redshift. The argument he was making was that it's actually pretty...
How are you? I just want to say hi. I'll see you next week.
Great, yeah.
I'm have to run.
Yeah.
We'll have coffee.
I wanted to just let him know where my office was and meeting with him next.
I can bring him up.
Thanks. So it's at 2 o'clock.
2 o'clock.
Yeah, I just wanted to let him know the general direction.
Okay.
Very excited. Okay. Yeah, it's very cool. I want to talk to you about
You don't have any time on Friday later in the day?
next week. Okay, great.
Hey, Andrew, I just wanted to say my office is upstairs.
Okay.
My name is
Mia. Yeah, no, I know you.
Okay,
I saw you at Berkeley.
Okay.
I don't know that we ever sort of met, but...
Okay. Well,
are you going to the reception at 5:15? He will also be there, so you could also talk to him.
He's right here in
Perfect. Okay,
Okay.
See you later.
I just wanted to say hi, I'm Sandy Stefano.
Oh, hey, nice to meet you.
Yeah, you too. I'm really pleased. Unfortunately, we won't have an actual appointment together.
Oh, okay. But we're going to have dinner.
But we're going to have dinner.
That's better.
I'm looking forward to
There's
talking
wine
to you then.
involved then.
Sounds great. We'll talk about the real deal.
Yeah. Great. Yeah, okay, thank you.
He's a prospective student who's conducting a survey for Jupiter's cluster.
Actually, that's the CF one.
We could be game things. If they, in fact, we don't even get to choose wherever the lens is.